Ishmael, Sophia, and me, Eugene, uh, we are going to be talking about the coefficient of determination and standard error of the estimate. This is section 10.3 in the lecture notes. So to start off, the coefficient of determination is going to be a number that's between 0 and 1, but it's often expressed as a percentage. So instead of saying 0.85, you would say 85%. It can help achieve the standard error of an estimate, and finding these values can lead to a better understanding of relationships between different variables that might not actually seem related to each other. I'll talk about that later in the applications slide. So an important term that I'm going to need to explain is total variation, which is the sum of the squares of vertical distances between the points of the mean, as shown here. And its formula is, as you can see, the sum of all of y prime minus the average y, and then that squared. It's not actually y prime. It's just that's the the little symbol for it. And the unexplained variation is, as you can see, just y minus and then y and then the little prime symbol. So the coefficient of determination is, oh, something's happening, is denoted as r squared, which is the ratio of predictable variation to total variation. And the coefficient of non-determination is denoted by 1 minus r squared, which is the ratio of unpredictable variation to total variation. So if you had, let's say, 0.85 as your coefficient of determination, the coefficient of non-determination would be 1 minus 0.85, which would leave a 15%. Another two important terms are the prediction interval, which are a variable's interval estimate. In the example later, I can explain that a bit better. And the standard error of the estimate, which is the standard deviation of result values from the predicted result value. So it's essentially saying, let's say you predict a result value of 100, but there's going to be some standard deviation from 100, so it's going to be a little bit off from it. You can predict that standard deviation. Like, so you can predict if you'll get 102, 101 using the standard error of the estimate. So we have a very complicated formula here for the prediction interval. It gets broken down into a lot of smaller parts, but as you can see, it's it's an interval. So you have on your left side this, and then y minus. On the right side, you have y plus, and all that. So an example we have here is the director of an alumni association for a small college wants to determine whether there is any type of relationship between the amount of alumnus contribution in dollars and the number of years the alumnus has been out of school. The data follows here, as you can see. The regression line equation is y. I'm just going to call it y prime. Y prime equals 480.610 minus 50.854x. Because it's a slope. So that's how the regression line works. The correlation coefficient is r equals negative 0.931. As you can see, also it's fine if it's negative here because it's just r. R squared though will end up being positive and between 0 and 1. So we compute the standard error of the estimate rounded to at least 2 decimal places if appropriate, and we have to assume that the level of significance is 0.05. So as you can see, we have sample size of 5, degree of freedom, so we have 2 different variables, so -2, 5 minus 2, 3. We have a z-score here as well, based off of these calculations and given R value. So for a significant relationship, so for us to be able to say something is related to something, for a value of R greater than plus 0.878 or less than negative 0.878 is needed. And since the value of R plus or minus 0.931 is less than this, the null hypothesis is rejected. So the standard error of the estimate should be calculated. There are 2 methods for finding the standard error of the estimate, by the way. So the first method is using this formula here, where we get the standard deviation of the estimate, and that's equal to the square root of the sum of y minus y and prime, or yeah, squared divided by, and then the degrees of freedom, or n minus 2. And as you can see right here, that all the numbers are plugged in already. So it's the sum of, well, it's some of these actually. I was going to say some of these squared, but it's actually also already done right here. And divide that by 3, and the square root of that is 80.59. So that's the standard deviation of our predicted values. So we have a second method. We're going to use the same numbers from the previous equation, but as like an example of a different method is using a different formula, as you can see here, where it's the sum of y squared minus a, which would be this primary, this number right here that I'm circling, and then times the sum of all y minus b, and then times that all by the sum of all the x's and y's. So it's better outlined here, but sum of all y's squared, so all of these minus that initial number I pointed out before, times 1030, or all these combined, or 1030, minus, and then negative 50.854, which is the second number in here, as you can see, and it's negative because it's being subtracted from 480. And then you times that by xy, the sum of all the xy values, which ends up being 3060, and divide that by the degrees of freedom, which is 3, and the square root of it all ends up being 80.59, which is the same as in the previous example. So in this case, the standard error of the estimate, the standard deviation of the observed values around the predicted values is 80.59. An application of these correlations in real life could be seen with economics, actually, where there's the relationship, the well-known relationship of supply and demand has its coefficient of determination, where like a change in supply of a product will also change its demand, and an experiment that could be conducted to see the effects of an increase in supply will have on demand for a product. Thank you so much for watching. I hope this presentation has been enjoyable. And yeah, thank you very much.